So for problem 3, we're going to focus on this video on how to find limits using the calculator and using tables that a calculator features. Now, this method of using tables is actually a very wise and sly method. I remember helping a student at the college with second semester calculus, and they were trying to do a certain problem in a very particularly difficult way. And I said, hey, why don't you just use tables, and we were able to solve it really quickly. So this is a very weird approach to math, but this is a very true approach to math. So let's start with the first one, and I'm going to use Desmos in our presentation. So we're looking for the limit of 3x squared as x approaches 4. This means that what happens as I get closer and closer to 4 from the left and also from the right. So let's see. So let's do this. And we're going to use a table. So I'm going to click on this function that I made, 3x squared. I'm going to click on the edit list, and I want to have the option to create a table. And so it does it for us automatically. But what we're going to do is we're looking at the x. These are the ones that we're going to mess with, and it'll automatically give us the y values. So I want x equals 4. I'm going to put 4 in the middle right here. So usually the way you do this is you put the one that you want, the limit that the x is approaching, right here, and then you'll put the numbers right before it in the other spots. So this will be 5 and this will be 6. Now, this is actually pretty nice because you'll notice that it's not undefined, right? So limits are usually used to predict something that's not there. But in this case, if I plug in a 4, it's going to be 48. There's no hole there, okay? And if you look, we can even look on this graph, and you would see that, where is it? 448. 448, there it is. So notice that when x is 4, it's not undefined, it's actually a y value of 48. So this is a very nice problem. It's kind of rare for this to happen to us, but what we're saying is the following, that f of 4 is actually defined at 48. And on top of that, the limit as x approaches 3x squared is also 48. So we kind of like that with this first problem. We're going to see the same thing happening with this second function, right, for part B. And we're looking at the limit as x approaches 3 for the function 4x squared. So again, we're going to take our table, 3, 4. This is easier on a real calculator, but we're going to use what we have. And again, this is surprising for us because there's no undefined. So the limit as x approaches 3. So what I'm saying is, like, from the left, these numbers are approaching 36. From the right, these numbers are approaching 36. Now you're going to think to yourself, well, that's a big stretch, right? How do we go from 4 to 16 to 36? Well, I agree with you. So let's change these numbers, right? Like, what if I did, instead of 2, we did 2.8, right? And instead of 4, right, we're gonna make the time frames closer. Well, we're gonna get as close to 3 as possible without writing 3, right? So let's say 3.1. Okay, notice now as I do that, the gaps are getting closer. Like, these numbers are a lot closer to 36. What if I change this to a 3.01? Oh snap. Or what if I change this to a 2.99? Do you see how we're closing that gap? It's like with Archimedes and the shapes, the polygons, right? As we add more size, we're closing the gap. As we get closer to the buffer frame, we're closing the gap. So by doing that, right, I could add more numbers, and all of a sudden, I could even trick it, right? I could trick the Desmos, the calculator, to tell me, oh, it's actually 36, right? I never typed in the number 3 here, and this is not 3, this is 3.0001. But I pretty much fooled the calculator to tell me, hey, pick a number between 36 and 36. Good job, 36. So, for this problem, f of 3 is 36, but so is the limit. Okay, and that's because it wasn't undefined. Ah, part C. This one's a beauty. So, let's go ahead and add a table to this one. We're interested in 0, and you'll note already that we're into some problems. So, this one is saying undefined. Question to you is, okay, so obviously there's a hole. Obviously, for this function, f of 0 is undefined. That means I put money into the vending machine, and the machine didn't do anything. It didn't spit anything out, no money back, no chips, nothing. It's undefined, doesn't know what to do. Okay, so let's look at what it's leading up to. Well, 0.45, 0.84, 0.45, 0.84. Fascinating. You know what we could do, right? We can definitely, let's get as close to 0 as possible. So a little bit past 0 might be 0.1. Right? Or right before 0 might be negative 0.1. Right? Let's make this negative 0.2, so you maybe see this could be 0.2. So all of a sudden these numbers are getting closer and closer to something. We could add a 0 to this. We could add a 0 to this. Right? We're closing that gap. We're getting closer to 0. Why are we going towards 0, Mr. Over? Where did you get this? This is what we're looking for. Okay? We want to see what happens at 0. We know that it's undefined. We're driving down this road, and when we get to this point, there's no road. There's nothing there. So we have to use a limit to predict what should be there. That is not there because it's undefined. So what I'm doing is I'm getting as crazy close as possible without being there to see what it should be there. So what if we add more zeros, right? What is happening here? What number am I getting closer and closer and closer to? Now, I need you to notice that in all these cases so far, everything has agreed, right? It becomes kind of like a silly game. Pick a number between 1 and 1, because that's what this should be. Okay? So the limit is 1. You're not going to be able to, you're not going to get this through any algebraic way. So if you're thinking, okay, Mr. Or is there a formula I can do? Or can I do something to solve for x? It doesn't work out like this. This is a very different mathematical approach. This is good calculus and, you know, real mathematics and science is about. It's kind of just using the tools you have to kind of approach things to see what's going to happen. Now, so we went ahead and used a calculator, right? We closed this gap. We made this as close as possible to the 0 that we're interested in, right? The 0 coming from here. And we pretty much did it in such a way that, you know, we pretty much tricked Desmos into telling us what the limit is. So notice that from the left, it's approaching 1. From the right, it's approaching 1. And so this has to be 1. Not the actual value, but the limit, the prediction. What should be there is it should be a 1. So what we're saying is if x is 0, there should be a 1. If x is 0, as x is approaching 0, from the left and from the right, there should be a 1 there. That's what the limit is doing for us. Now, we're starting you off easy on limits that actually work. And I'm going to explain that a bit after we look at this one. So here's h. Let's look at the table for that. And this is nice because we're looking for 0. And so it's already set at 0 for us, right? We see that it's undefined. So we know that for this function, f of 0 is undefined. Great. Well, we know that, but that doesn't do us much good. What should be there? What is the prediction of what should be there if something were there? Well, this is kind of getting weird because from the left, I'm getting these numbers that are getting smaller, right? 0.7, 0.4. And then from the right, it's coming from the negative, right? Like negative 0.7, negative 0.4. So we kind of need to get a little closer, close the gaps. We want to get as crazy close to 0 as possible without actually using 0. So let's do that, right? Let's start adding decimals. So let's do 0.1, negative 0.1, and a 0.1. And we notice that it's getting a little better. Let's go ahead and add some more zeros to this. Oh, scientific notation. Interesting. Oh, snap. Okay. Same here. Ah, okay. So again, we're not using like, we're getting crazy close. We can't use the actual value of 0, but we're getting as close as possible. And if we do that, we end up getting between 0 and 0. So pick a number between 0 and 0. Well, gee, 0. Now, notice that these two values agree. They're the same. So we're saying that from the left, right? If we look at this graph, from the left, I'm traveling this road. This is what from the left means, right? I'm traveling this road along the x-axis. And as I'm traveling this road, I'm getting closer to this destination. From the right, I'm getting closer to this destination. When I get there, there is no destination. But what I do expect is that it should be a 0. When x is 0, this should be, right? Should be that if x is equal to 0, then y would equal to 0. It should be, but it's not because it's undefined. It's undefined. However, traveling on this graph, traveling on this road, looking at the table, looking at the data, it's saying, hey, it's going to be between 0 and 0. So you might as well call it what it is, a 0. But that's the limit. Okay, the limit is going to be 0. Now, some point very soon, these two numbers are not going to agree with each other. They're going to be different. And when that happens, we'll talk about it. Okay? But for now, if these are agreeing, then we have a limit. All right?